permits, we will discuss double Roman domination in Cartesian product. I assume all of you know the basics of domination. Domination is considered to be one of the fundamental concepts in graph theory. Various domination parameters can be defined by combining domination with other graph theoretical parameter. Roman domination is one such variation. More than 70 such variations are listed in the book by Fundamentals of Domination in Graphs by Teresa W. Haynes et al. The study of Roman domination was originally motivated by defense strategies used to defend the Roman Empire during the reign of Emperor Constantine the Great. Emperor Constantine had to decide where to station his 4 army units to protect his 8 regions. He has to place the army units so that every region was either secured by its own army or was securable by a neighbor with 2 army units, one of which can be sent to the undefended region directly if a conflict breaks out. Okay. Ian Stewart, in his article published in 1999, discussed a strategy of Emperor Constantine for defending the Roman Empire. Later, in 2004, this concept was introduced in graphs by Cockayne et al. I will give the mathematical definition for Roman domination. A Roman dominating function, RDF, is a mapping from the vertex set V to the set containing 0, 1, 2, such that every vertex with the value 0 must be adjacent to at least one vertex with the value 2. Okay. For any graph, we can find a RDF because simply assign the value 1 or 2 to each and every vertex. But we are interested in minimizing the value. The total value, sum of the values of the vertices, is known as the weight of a RDF. Hence, we are interested in it is known as Roman domination number, which is denoted by gamma RG. Consider this example. We have to give the values 0, 1, 2, such that a vertex with the value 0 must be adjacent to at least one vertex with value 2. We have to minimize the total weight. So it is feasible to assign the value 2 to this vertex, so that we can give 0 to all the neighboring vertices. There is one more vertex remaining. We have to give at least 1 to this vertex, so that for this RDF, the total weight is 3. We can easily check that this is the minimum possible value, so that for this graph, gamma RG is equal to 3. Now, there are many variations for Roman domination. Independent Roman domination, that means the...
No, in the previous example...
Sir. Yes, sir.
No, in the previous example, you put 2 and 4 zeros and you put 1 for the last leaf.
Yeah.
Can we not put 2 or 0 there?
Pardon, sir?
In that place of 1, can we not put 2 or 0?
If it is 0, then this 0 vertex is not adjacent to a vertex with value 2. So 0 is not possible. But if it is 2, the weight will increase.
Okay.
Okay.
So 1 is used only to minimize the weight.
Yeah. In some other cases, 2 may be feasible. More efficient, 2 may be reasonable.
No, but if Roman domination number is minimum, then we have to put 1 only.
In this case, we have to give one only.
Okay.
Thanks. There are many variations for Roman domination. Yeah.
Jignesh Chaudhary bhai has raised his hand.
Yeah.
Hello. Hello.
Sir.
Madam, it is necessary we have to assign by 0, 1, 2.
Yeah. Mapping is from the vertex set to the set 0, 1, 2.
If we assign by ABC, then it is possible or not? It is an arbitrary number.
No. It is defined like that. We have to give the value 0,
those
1.
Those are adjacent to a particular vertex. It is denoted by 0. It is assigned by 0, na?
Sorry?
You assign first you assign a vertex as a 2.
Yeah.
Then all the adjacent to this vertex is assigned by 0.
Yeah.
Okay, and rather than assigned by 1.
If we assign 1 to these vertices, that will increase the total weight, sir. We have to minimize the total weight.
Okay. Now, I think maybe if we want to assign by -1, is it possible?
No, it is another Roman domination. It is another concept, different concept.
Okay, thank you, ma'am. Okay.
Anu, does there any significance for these numbers 0, 1, and 2?
Yeah, 0 corresponds
Domination
to.
is.
0 corresponds to a region where there is no army unit. 1 corresponds to a region where there is 1 army unit, and 2 corresponds to a region where there are 2 army units. So, if there is any attack, yeah. Okay. Shall I continue?
So, yeah, sure.
Independent Roman domination is one such variation. In this case, the vertices with the non-zero values should induce an independent set. Another variation is weak Roman domination. In this case, a vertex with the value 0 must be adjacent to at least one vertex with the non-zero value. There is no restriction that this vertex must be assigned the value to. Only non-zero value is enough. Another variation is total Roman domination. In this concept, mapping is similar to Roman domination, but the vertices with the non-zero value induce a subgraph which has no isolated vertices. Another variation is signed Roman domination. In this concept, the mapping is from vertex set to the set -1, 1, 2, and some conditions. And we focus on this one, double Roman domination. All these areas are very good, and we can do research on this. We will discuss today on double Roman domination. The concept of double Roman domination was introduced by Robert A. Beeler, Teresa W. Haynes, and Stephen T. Hedetnimi in 2016. This concept doubles the protection by ensuring that any attack can be defended by at least 2 legions. But the increase in the cost is not doubled. That is the benefit. I will give the formal definition. In this case, our mapping is from vertex set to set 0, 1, 2, 3. And there are 2 conditions. If the value of a vertex is 0, then this vertex must be adjacent to at least 2 vertices with the value 2, or at least 1 vertex with the value 3. Second condition is that if a vertex with the value is equal to 1, then this vertex must be adjacent to a vertex with the value at least 2. So, we have to take care of vertices with values 0 and 1. Such a function is called a double Roman dominating function. In short, DRDF. As in the case of Roman domination, we are interested in DRDF with a minimum weight. Sum of the values of the vertices is known as weight of a DRDF, and a minimum weight of a DRDF is called a double Roman domination number, which is denoted by gamma DRG, and a DRDF with the minimum weight is called a gamma DR function. Okay, we can illustrate with one example. Consider C7. We have to assign values 0, 1, 2, 3. Vertex with the value 0 must be adjacent to either a vertex with the value 3 or two vertices with the value 2. A vertex with the value 1 must be adjacent to a vertex with a value greater than or equal to 2. So, all the two conditions are satisfied here. Total weight is equal to 8. We have a theorem for cycle. This is the minimum possible value. We can reassign the value in such a way that this value 1 is not used. How is it possible? We can reassign this value as 0 and reassign this value as 3. In this case also, each vertex with the value 0 is adjacent to at least one vertex with the value 3. So our condition is satisfied. This is possible for any gamma DR function. That is, we can omit the value 1 without changing the total weight. This is very useful result in determining the gamma DR of any graph. It is proved in the base paper. In a double Roman dominating function of weight gamma DRG, no vertex needs to be assigned the value 1. So, now onwards, we have to take care about the vertices with the value 0 only. Vertex with the value 0 must be adjacent to at least one vertex with the value 3 or two vertices with the value 2 each. Okay. Some simple observations are there. Let me ask, is there any graph with the gamma DR is equal to 1? Is it possible? Is there any graph with the gamma DR is equal to 1? No.
Not possible.
Not possible. Because the vertex with the value 1 must be adjacent to a vertex with the value greater than or equal to 2. So it is not possible. That is, for any graph, gamma DR is greater than or equal to 2. Another thing, for which graph gamma DR will be 2? There is only one possibility. It is for K1 only. Yeah. For all other graphs, gamma DRG is greater than or equal to 3. When it will be equal to 3, if and only if the graph has a universal vertex. That means a vertex which is adjacent to all other vertices. In that case, we can give the value 3 to that universal vertex and 0 to all other vertices. Okay. Now, for a totally disconnected graph, that is a graph without any edges, Kn complement. In that case, we have to give at least 2 to each and every vertex so that gamma DRG is equal to 2n. Now, consider the case complete bipartite graphs. K1n, it is, can you see the screen?
Yes. In
the case of K1n, it is similar to the graphs having a universal vertex. So I can give the value 3 and 0 to all other vertices. So in this case, gamma dr will be 3. Now, K2n minus 2. In one partite set, there are 2 vertices, and in the other partite set, any number of vertices. What will be the optimum value?
Six.
No, we can reduce the value. Vertex with the value 0 should be adjacent to at least 2 vertices. Yes, we can give 2 to each these vertices and
Rest
0.
are zeros.
Yeah, 0. So each vertex with the value 0 is adjacent to at least 2 vertices with the value 2. That is gamma dr of K2n minus 2 is equal to 4. If the partite set contains at least 3 vertices, then what will be the value?
6.
In this case, we have to give at least 1 vertex, 3 in this partite set, and also in this partite set also we have to give 3 to at least 1 vertex, and all other vertices 0, so that gamma dr will be equal to 6. Okay. Now, what will be the gamma dr of cycles? C3. It is trivial.
2.
2 won't work.
4.
We don't need 4. It has universal vertex, isn't it?
Okay,
So
okay.
we can give 3, then 0 to all other vertices, so that gamma dr is equal to 3. What about C4? 4. We can give 2 to alternate vertices and 0 to other vertices. 0 vertex is adjacent to 2. Therefore, gamma dr of C4 is equal to 4. What about C5?
Okay. 2. 5.
Yes, 5.
Yeah.
No. It won't work. 6. We need 6. Okay.
Wait.
Yeah, 6, correct.
Yeah. It is 6. What about C6?
6.
Yes, again it will be 6. Okay. So, by these examples, we can prove a theorem. Proof is a little bit difficult. The theorem is gamma dr of Cn is equal to n if n is a multiple of 2 or 3. N plus 1 otherwise. Okay. Now, what about path? P1 we have already discussed. It is 2. P2?
It is also 2.
No. Two won't work, sir. Because in that case, we have
0,
to give
3 you have to put.
Yeah, 0, 3. Gamma dr will be 3. For P3, 3 will be enough.
3.
Okay. But for P4,
6.
yeah. We don't need 6.
Then you will have to go to 4. No?
No 4.
5.
5. Okay. Again, for P4, we have the theorem gamma dr of Pn is equal to n if n is a multiple of 3 and n plus 1 otherwise. Okay. Yes. We have discussed all these graphs KPQ. Now, what is the benefit of double Raman domination over Raman domination? We have already seen the example. For star graph K1 n minus 1, gamma dr is equal to 3. But gamma r, in that gamma r, we have to give only 2 to the central vertex. That is, in practical situation, we are doubling the difference, but the cost is not increased more than 50% of the original cost. Another example is K2 n minus 2. We have seen that gamma dr is equal to 4 and gamma r is equal to 3. That is, we can double our difference with an increase in expenditure of only 33%. Then it will be more beneficial. Okay. Now we can discuss some basic theorems in double Raman domination. We have already discussed the double Raman domination number of a cycle is n if n is a multiple of 2 or 3 and n plus 1 otherwise. And the double Raman domination number of path will be n if n is a multiple of 3 and n plus 1 otherwise. Now, we have already seen that gamma drg is equal to 3 if and only if G has a universal vertex. That is, maximum degree is equal to n minus 1. When it will equal to 4? Gamma drg is equal to 4 if and only if G is the join of K2 complement and H, where H is a graph with the maximum degree less than or equal to cardinality of H minus 2. Okay. Also, there is characterization for graphs with the gamma drg is equal to 5. This happens if and only if maximum degree is equal to n minus 2 and G not equal to K2 complement join H for any graph H of order n minus 2. Okay. But for all other values, the problem is open. Now, bounds for gamma dr in terms of order and diameter. Let G be a graph with the n vertices and diameter d. Then double Raman domination number lies between d plus 1 and 2n minus d. These bounds are sharp. There is examples. Take the path on n vertices where n is a multiple of 3. Then it will satisfy the lower bound. And by attaching a pendant vertex to the third vertex, then it will satisfy the upper bound. Okay. In the base paper, there is an upper bound in terms of order. It was like this: gamma drg is less than or equal to 5n by 4. The above theorem gives a better upper bound when the diameter is at least 3n by 4. Okay. Now, there is Nordas-Gadam type inequalities. Let G be an n vertex graph and n greater than or equal to 3. Then the sum of gamma dr of G and G complement will lie between 8 and 2n plus 3. There are graphs which attains lower bound and upper bound. Equality holds for the lower bound if and only if G or G complement has a vertex of degree n minus 1 and its complement has a vertex of degree n minus 2. And equality holds for upper bound only when G or G complement is KL. Now, this is another interesting result. That is, there is no relation between the double Raman domination number of a graph G and its induced subgraph. In all domination parameters, such results are there. Given any two positive integers a comma b greater than or equal to 3, there exists a connected graph G and a connected induced subgraph H of G such that gamma drg is equal to A and gamma drh is equal to B. We are considering only A comma B greater than or equal to 3 because all other cases equal to 1, 2, they are trivial cases. That's why we are taking A and B are greater than or equal to 3. The proof is by construction. That is, we know the gamma dr of some known classes. Then we are manipulating those structures in such a way that gamma drg is equal to A and gamma drh is equal to B. The proof is very lengthy but simple. I will show one example. If both A and B are multiples of 3, then we can take the path on n vertices where n is a multiple of 3. If now this case is, yes, the graph G has double Raman domination number a multiple of 3, and we have to get a subgraph for which double Raman domination number is a multiple of 3 plus 2. In this case, we are constructing like this. These techniques is applicable for all values. Okay. Now, some open problems. The same problem, it is mentioned by Professor Armugham and Dr. Sidhu Varghese. That is, let G be a connected graph and H be a connected induced subgraph of G. Under what conditions gamma drh will be equal to gamma drg? Gamma drh will be less than gamma drg and gamma drh is greater than gamma drg. Okay. Now, in the base paper, Robert A. Beeler et al. Posed a question. Classify the graphs. Find the classes of graphs which satisfy the inequality gamma drg less than or equal to n. From this discussion, we can give partial answer to this question. Cycle Cn with the n is a multiple of 2 or 3. For those graphs, gamma drg will be less than or equal to n means equal to n. Also path with the n where n is a multiple of 3. Then any graph with a universal vertex and n greater than or equal to 3. Then any graph with a pair of twin vertices. Twin vertices means the vertices having the same neighborhood, each of which dominates all other vertices like K, 2, Q. In all these cases, we will get gamma drg is less than or equal to n. Now, we will discuss the relation of double Raman domination number with the domination number and Raman domination number. For any non-trivial connected graph G, gamma Rg less than gamma drg less than 2 gamma Rg. Equality holds only when the graph is trivial, that is Kn complement. Another relation between double Raman domination and domination. For any graph G, 2 gamma G less than or equal to gamma drg less than or equal to 3 gamma G. This upper bound is very trivial because take any dominating set and give the value 3 to each vertex in the dominating set, so that gamma drg will be equal to 3 gamma G. But the lower bound, to prove the lower bound, it is little bit difficult. Now, the graphs which attains the lower bound, we can give a characterization in terms of two domination number, gamma 2g. Gamma 2g means the minimum cardinality of a set S such that every vertex in V minus S is adjacent to at least two vertices in S. In terms of gamma 2g, we can give the following characterization. For any graph G, 2 gamma G equal to gamma drg if and only if gamma G is equal to gamma 2G. Okay. But for tree, this lower bound can be improved by 1. For any tree, 2 gamma t plus 1 less than or equal to gamma drt less than or equal to 3 gamma t. This lower bound is improved by 1. Also, there is realization for all these values. Okay, that is any ordered pair. Sorry, this realization is for another theorem. An ordered pair AB is realizable. Yes, for this theorem is realizable as the domination number and double Roman domination number of some non-trivial tree if and only if B lies between 2a plus 1 and 3a. Each value can be realized as a graph. Now, we have already in literature this inequality, relation between domination number and Roman domination number. Gamma G less than or equal to gamma Rg less than or equal to 2 gamma G. Now we have this inequality, 2 gamma G less than or equal to gamma drg less than or equal to 3 gamma G. Graphs for which gamma Rg equal to 2 gamma G are called Roman graphs. Similarly, characterize the double Roman graph, or in particular, double Roman trees. A paper got published in which they characterized a special class of graphs, that is generalized E3KK will be a double Roman graph if and only if K is a multiple of 3 or K is equal to 1 or 4. But the general problem is still an open problem. Now, we will study the impact of some graph operations on double Roman domination number. If we add an edge, like U and B be two non-adjacent vertices, and we are adding the edge UV, then the double Roman domination number will be decreased by at most 2. In some cases, the double Roman domination won't change. In some cases, it will be reduced by 1, and in some other cases, it will be reduced by 2. In the same graph itself, we can see all these examples. This graph G is a graph with a gamma dr edge. If we adding these two vertices, then the gamma dr is decreased by 2. If we adding these edge, it is reduced by 1. If we adding these edge, it won't change. Okay. Also, we can prove that given any two positive numbers A and B, where A minus 2 less than or equal to B less than or equal to A, there exists a graph G such that gamma drg is equal to A and gamma dr of G plus UV is equal to B. It is a simple proof. Now, there exist graphs for which addition of any edge will decrease the double Roman domination number. P4 and C4 are such graphs. Also, there exist graphs for which addition of any edge will not change the double Roman domination number. P6 and C6 are such graphs. So our next problem is characterize such graphs. Addition of any edge won't change the gamma dr. Addition of any edge will decrease the gamma dr. Okay. Now, addition of twin vertex. There are two types of twin vertices. A false twin of a vertex U is a vertex U dash, which is adjacent to all the neighbors of U. And a true twin of a vertex U is a vertex U dash, which is adjacent to U and its neighbors. That is the closed neighborhood of U. Okay. We can prove that by adding a true twin, gamma dr will increase by at most by 1. But if we add a false twin, then gamma dr will increase at most by 2. Now, the Nasal scan of a graph. How can we construct Nasal scan? Let G be a graph with the vertices U1, U2, etc. Un. Corresponding to each vertex Ui, we are adding a vertex Vi and make adjacent with the neighbors of Ui. And add another vertex W and make adjacent to all the newly added vertices V1, V2, etc. Vn. The resulting graph is known as Nasal scan of G and it is denoted by mu G. We can prove that for each graph G, gamma dr of mu G is either gamma drg plus 2 or gamma drg plus 3. In this case also, the upper bound is very trivial because already there is a gamma dr function for G. We are adding new vertices V1, V2, etc., Vn and W. In that newly added vertices, W is adjacent to all the vertices V1, V2, etc., Vn. So we can give the value 3 to W. So that that will a drdf gamma dr function for mu G. So the upper bound is very trivial, but to prove the lower bound, it is very difficult. And there are graphs which attain upper bounds and lower bounds. For example, P2. P2 gamma dr is equal to 3. What is the Nasal scan of P2? Nasal scan of P2.
C5.
C5. Okay. What is the gamma dr of C5? We have already proved it is 6. That is, P2 satisfies the upper bound. We can verify that all paths satisfy the upper bound, but we couldn't prove that result. Also, for bi-star, those graphs attains this lower bound also, but characterization for such graphs is still open. Now, double Roman domination in Cartesian product. Let me define the Cartesian product of two graphs. It is denoted by G box H. The vertex set of G box H is the Cartesian product of vertex set of G and H. Two vertices U1, V1 and U2, V2 are adjacent in G box H if the first coordinates are equal and second coordinates are adjacent in H, or first coordinates are adjacent in G and the second coordinates are equal in H. Okay. Consider these two graphs. the Cartesian product will be like this. Okay. Now, we have already seen that for every graph G, gamma drg is greater than gamma rg. Also, it is well-known result in Roman domination. Gamma r of G box H is greater than or equal to gamma G into gamma H. I forgot to add the reference here. So combining these two, we can say that gamma dr of G box H is at least the product of domination number of G and H. Now, look at this inequality. Here, V0, V2, V3 means the set of vertices with the value 0, 2, 3 respectively. We have already seen that we don't need the value 1. That's why we are omitting the vertex set V1 here. We can prove that cardinality of V3, that is the number of vertices with the value 3, is less than or equal to gamma drg minus 2 gamma g. Also, we can prove that cardinality of the vertex set with value 2 is greater than or equal to 3 gamma g minus gamma drg. Using this proposition, we can find this inequality. That is, gamma dr of G box H is at least gamma J into gamma drh by 2. Now, from this inequality, we can arrive at this corollary. Gamma dr of G box H is greater than or equal to gamma drg into gamma drh by 6. But these inequalities are not strict. So, we strongly believe that we can improve these bounds. This theorem is valid for any domination parameters. Gamma dr of G box H is less than or equal to minimum of n2 into gamma drg and n1 into gamma drh, where n1 and n2 are the orders of G and H. Now, for special Cartesian product graphs, grid graphs. If the factor graphs are paths, then the Cartesian product will be known as grid graphs, and it is denoted by GMN. Here we are giving the figure G2N. This is G21. G22 is not here because G22 is C4 and it is already discussed. For other values, n is equal to 3, 4 and 5. Here, the black vertices denote the vertices with value 3. And this gray vertex denote vertices with value 2. And the empty circle denotes the vertices with the value 0. This is optimum assignment for grid graphs. We can prove that for the 2 by n grid graphs where n not equal to 2, gamma dr of G2n is equal to floor function of 3n plus 4 by 2. These are our major references. This is the fundamental paper in double Roman domination by Robert A. Beeler, Teresa W. Haynes, and Stephen T. Hedegnini. Thank you. Now.
Yes, thank you, Anu. That was a lovely talk. Now the forum is open for questions. Anyone? Yes, Agnes. Agnes has raised her hand. Please, Agnes, would you ask your question?
Hello.
Yeah, Agnes.
Okay, it was mentioned earlier, like Roman domination, the application is like based on the army and legion, right? Like whenever
Yeah.
there is a legion with no army, like a legion from two, having two armies will like provide with one.
Yeah.
How about like in this, it is like the function values are 1, 0, 1, 2, 3. And whenever there is a legion with one army or one army, why it should be like adjacent to a legion with more than two armies? Like it is already protected, no? Is it like
Yeah.
double protection or more
Yeah.
protection?
We are interested in double protection. Each
But is it
region
like
must be.
But I have read some other paper based on like different types of securities, something like that, how to distribute all those different types of security among the vertices, rainbow domination or something like that.
Yes, I have heard this, but I don't know the exact definition for that
So
domination.
is it like this three is like different types of armies or the same concept? I just want to know the concept.
I have no idea about rainbow domination.
I'm not sure it is rainbow domination or not.
We can look at the literature. I have no idea.
No, I think it is K rainbow domination or something like that. Total K rainbow domination. They have said like there is different when it is like K is the number of different types of armies or securities, and how do you distribute it among the vertices? Like some vertex will have all the three types of armies. In some there will be like four vertices, four armies. Something. Is it something like that? I know. I'm just asking.
In double Roman domination, each vertex without an army should be protected by neighboring two army units. That is the concept in
That is
double Roman domination.
No, that is Roman
Double.
domination. No? In
Roman
double should be
double each region without any army unit must be defended by, I mean, must be adjacent to two army units.
No, is it like two vertices with two armies each?
Whenever this army unit came to this undefended region, there should be one remaining.
No, according to definition, one vertex with the function value 0, it should be adjacent to at least two vertices with two function value 2 each.
Yeah.
Right?
Yeah.
So that is basically two. It should be adjacent to two legions with two armies.
Yeah.
Okay. Okay. So you are trying to like ignore that, like it would be better if there are no legions with one army, because you will have to.
We can reduce to that situation.
Okay. Is it all like okay? Thank you.
Right. Anyone else with questions?
Anu, could you please explain how this concept is directly related to the domination concept? Because I didn't get it actually. That's why I'm asking. The assigned vertices need not, that is not a minimum dominating set or something like that, no?
If there is a minimum dominating set, we can assign the value 3 to each that dominating
that's what
vertices.
you told in the case. Yeah, that's what you told to get the upper bound by domination. That I understood. But directly when you define the domination, any domination.
There is no dominating set coming.
That's what I asked. Okay. Thank you. But why that name is given in literature? Any idea?
It is something like dominating. That means each zero vertex is dominated by, that means adjacent to a vertex with two vertices with the value 2. There is a similarity in that dominating concept.
Okay. No need of actual domination in graph.
No.
Okay. Thank you, Anu. Thank you.
Yes, more questions? Anyone?
But still, we are comparing, like there are relations with domination set only, no? If there
Yeah.
is no much relation, then why do we find relation between domination number and Roman domination number, or like double domination number?
If there is some relation already, these domination parameters are already studied. So
Yeah,
we
but
can
you
use
said
those.
no, you said like there is no particular relation. It is just like it is something. The definition something like seems to be something related to domination only. That's why it was given the name domination. But then why we have to find relation? Like you said, like domination set is less than or equal to double. Like there is a Roman graph. Like
Yeah.
Roman domination number is less than or equal to 2 into gamma of g. Why do we have to find the such relations?
In some cases, that will help our double Roman domination concept. That's why.
Because the set is like it
Yeah.
is when you think no, there is no actual relation with it, no.
Anyway,
Like
we can use the concept of domination in some situations.
is it like the vertices in the dominating set can be given the value 2 or higher degree value function values like 2, 3, etc., something like that?
In some situations that will work, but in some other situations, to decrease the total weight, we have to think about some other vertices,
So
because
for
we are
find like
giving values.
if you are finding some algorithm to find the Roman domination
there
number or
are
something,
there
we
are
can use this
algorithms.
domination set.
Yeah, there are algorithms for some special classes, caudal graphs and co-graphs. Some
Like
special classes, there are algorithms.
To find the double domination number.
Double
So
Roman
that
domination number.
will this the dominating set will help, like you can give the values 3.
In some results, this dominating set and Roman dominating set will helpful.
Okay, so is it like you're giving the highest degree value, like highest function value to the domination set vertices?
Sorry?
Like 3, 2 is the highest function values, no? So you're giving that 3 and 2 to the vertices in the dominating set.
With the degree, higher degree. That will helpful.
Okay. Okay, thank you.
Any open problems can be suggested in this area?
In the talk itself, I have already mentioned that is find all graphs for which gamma DRG is less than or equal to n, and for the Miselskian graph, the value lies between gamma DRG plus 2 and gamma DRG plus 3. Characterize the graphs which attains those bounds. Also, for like other domination parameters, under what conditions gamma DRH will be equal to gamma DRG, where G is the graph and H is the induced subgraph, and less than. And
can you please show that slide once more?
At this point, characterizations are available only for graphs with the gamma DRG is equal to 3, 4, and 5. For all other values, the problem is still open. This point I have already mentioned. There is no relation between gamma dr of H and G. Under what conditions it will be equal, less than, and greater than.
Okay. Thank you. Thank you.
Is that all? Any more questions?
The previous result you have taken H to be an induced subgraph.
Yeah.
Why only induced connected subgraph? Why not any subgraph?
I think connected induced subgraph is more strong.
That is about the hereditary property or something like that. Am I right?
No. A general subgraph will be more general. The result will be holding for more subgraphs.
Yes, sir. What you said is correct. That induced is one kind of a problem. We can think about other subgraphs also. But connectedness is there because if it is disconnected, then the parameter becomes sum of each of the connected
Yeah,
components.
that's right.
No,
That
but
is why,
if you take disconnected graphs, the same thing is applicable for each connected component, right?
yeah, for each
Yes.
component also it is applicable.
Correct. Anu is Aparna's student, is it?
Yeah, sir.
Okay, okay. Thank you.
Thank
Yes,
you.
sir. My first PhD.
Good, good, good. I hope you remember me.
Yes, sir.
Yes, any more questions?
Ma'am.
Someone? Fatima? Yes?
Ma'am, I want to say vote of thanks. May I?
Oh, please do. Please do.
She can't wait for the last question.
So, I'm assuming there are no more questions. We'll go on to the next. Vote of thanks.
Okay, ma'am.
Fatima, please, it's over to you.
Okay. Good evening to all. I am Fatma, research scholar, University of Kerala, Karyavatam. I am so privileged to propose a vote of thanks to our respected speaker, Dr. Anu ma'am. Ma'am, your class is very interesting and useful to all beginners like me. Ma'am, in this talk, you explain how to find double Roman domination of some simple graphs. It helps us to understand the definition of double Roman domination. So, as a participant, I express my sincere gratitude to you, ma'am. Thank you, ma'am.
Thank you. Thank you all.
Thank you, ma'am. The academic sessions are over, and the next one is an informal feedback session. So let me invite the convener to say a few words.
Warm good evening to one and all. Before that, thank you, Anu, and thank you, Pramadamas, for chairing the session. So that was the end of our workshop, and we are coming to the feedback session, which is strictly an informal one. I hope you can hear me.
Yes, yes,
Still
yes.
clear.
Yes.
Yes, ma'am.
So while conducting a workshop in the online mode, everybody will have a feeling that it will be very easy to conduct it rather than conducting it in the offline mode. But it is not like that, as Vijuma sir mentioned in the introductory session itself, because we have to depend a lot on the internet gods and everything like that. So first of all, let me thank the internet gods for having no issues in any of our sessions. I mean, from the speakers end or from the organizers end. So thank you very much for, thank you for that one. Now, whenever we are conducting an offline workshop, why we have conducted a workshop is just because the workshops are always good for the beginners to start their research career. When I started my research, the workshops helped me a lot. But the main problem then I was facing during that time is I had to go away from my home. My child was small, so it was an issue. Now, when we are conducting it in the online mode, you all are sitting at the comfort of your home, so you can listen the class in a good manner, I think, rather than the offline mode. But definitely, when we are sitting at home, we do have so many things at our head, especially for ladies. So I understand that very much. Yesterday, one of my students told me that she wanted to ask something to the speaker, but at that same time, her child fell down and she has to quit from the meeting. So all those things happen in the online mode. I sincerely admit that. Even though there were 85 participants, 85 registered participants, we could meet only 55 to 60 participants in almost all the sessions. Now there are 69. That ranges. In the first sessions there were almost all, but in the next sessions the number was a little bit less. Some participants informed that they have some hospital cases and like that. Yeah, definitely that will be there. We have to understand that also. Now the feedback link will be provided at the message box. I think Nisha has done the forward. No, Nisha, please. Yeah, you can see the the feedback link at the message box. Please do click it, and you can give us the feedback through that. but we do expect some feedbacks from you, all of you. Over to you. Please switch on the video when you are giving us the feedback, please.
Hello, ma'am.
Hi, sir.
Good afternoon, one and all.
Yes.
Myself, Jignesh Musumia from Gujarat. It was my pleasure to participate in the international research workshop on graph domination. The workshop was great and I really enjoyed it. I'm impressed with the commitment and efficiency of those who have planned such an good events. Congratulate to all in one, especially Dr. Manju ma'am, who gave me such an opportunity to share my ideas among you. It is one of the best workshops which I have attended, and I am looking forward for the next year events. Thank you, all of you. Thank you.
Thank you, sir. Open to all.
Can everyone hear me? Yeah, 1 second. So, yeah, I'm Niranjan Krishna. I am a 12th standard student at Kendra Vidyalaya. It is quite unusual for somebody who is in high secondary school to attend these workshops, but still, yeah, I actually got into graph theory after reading Reinhard Diesel's book. So it has been pretty much going pretty well for me. And the reason why I attended this workshop was because I was kind of related with something I was reading at the moment. So I actually got this link from Douglas B. West's homepage. So there was this conference and I thought it was in Kerala. So it was pretty interesting and pretty cool. So that one workshop would be near my hometown. So that was a pretty cool moment. And then all the speakers were excellent in bringing out the ideas. And I enjoyed the workshop a lot. That's why I attended like almost every single session of them, because it was extremely an honoring moment for me to, at least hear these professional mathematicians like people like Dr. A. Vijaykumar sir and Dr. Sandy Closer sir and all of these mathematicians who are so excellent at their fields to give talks on graph theory. And one suggestion that I would like to make is that we could have included perhaps a problem solving session, something like, because I noticed that for almost every talk, there were a lot of open problems. And in the previous workshops I have attended, they have included these open problem sessions so that participants can interact with other participants more effectively and communicate with them. And there are already platforms like Discord and Microsoft Teams, which makes that possible. So that is one little suggestion that I have. But other than that, the workshop was I'm extremely privileged to attend this workshop, and I have enjoyed and learned from it thoroughly. Thank you.
Thank you, Niranjan, for that feedback. And what we have to say is that, the problem sessions were planned in between the sessions and the speakers have done their best. And from the organizer's part, we are not that much tech savvy. We don't know the technical terms that you have used just now. So that's a problem from our end anyway. Thank you very much for Niranjan. And what is your future plan, dear?
I'm thinking of pursuing, I'm taking like an entrance for the Cambridge and Oxford this year, in November. So it's like mathematics entrance test and TMUA. So, and also taking the CMI and ISI entrance.
Very good. All the best wishes, my dear. All the very best wishes.
Thank you.
Yeah, thank you.
Hello, ma'am.
Yeah, Vishna, please switch on the video.
Yes, ma'am. Okay. Hello. Okay. Good evening to one and all. My name is Vishna Devi, and I'm the participant of this workshop for the last 5 days. And before saying anything about the workshop, let me take this opportunity to thank, first of all, to Dr. Manju ma'am and all the authorities, college authorities who organized this wonderful workshop, especially students like us. So about this workshop, I must say that it was very beneficial. And initially, when I joined this workshop, I was not sure about that whether I will get understand or not, because it's not this graph theory is not my cup of tea. And before attending this session, I just went through this topic, and I got some interesting area. So it was my first time that I'm attending this workshop, especially on graph theory. And about the speakers, amazing speakers were there. And certain things were new for me, especially about open problem garden from Arumugan sir. He mentioned, and he teach in such a way that every beginner can understand about. Thank you, sir. And the next speaker was Professor Ampad Vijayakumar sir. I'm not the one who can say anything about his class. Excellent class and very respected person. Thank you, sir, for the wonderful session and all the other sessions. I really enjoyed, and every topic, starting initially it was like interesting. When it went to depth, I was so confused. I know it is lack of my knowledge. And all the sessions about the problem sessions on Seetu ma'am classes and all the foreigners classes, and especially today's class, Chitra ma'am, it was excellent. And Anu ma'am, thank you so much for introducing such a new concept as a beginner like us. And particularly if I talk about my opinion, I could take this workshop at ease because I was at home and had more time. So I would give a thumbs up for this wonderful session, and thank you so much, Manju ma'am, and all the authorities. Thank you so much. Thank you. Namaste.
Thank you, Vishnu.
Ma'am? Yeah, Amal. Good evening, all. Myself,
Please
Amal.
switch on the video, Amal.
My webcam is not working now.
Okay, no issues.
Okay. Good evening. Myself, Amal Pavitran, Faculty of Mathematics from the Cochin College. And I was a student of these great teachers. My feedback about this workshop, I came here with a little bit knowledge about domination graph theory. And right now, I'm leaving with a plenty.
Can you hear Amal?
No, miss.
No, something happened at his end, I think. Anyone, please? So you will receive the online certificate within 1 or 2 days. If you are not receiving the certificate within the next Wednesday, you please contact me via WhatsApp or mail. Definitely you will get the certificate after filling this feedback form. The feedback link is shared at the message box.
One small suggestion to convener, madam.
Yeah, tell me, sir.
Well done and good organization. And a personal thanks because you accommodated me after the last day. And in the feedback form, you have given only 3-point scales for rating the skills. I think 5 or 7-point scale is more desirable.
Okay, that we will keep in our minds for the future workshops.
Thank you.
Hello, am I audible?
Yes, Vinci. Yeah, please switch on the video. Yes, Vinci.
Hello, good evening to one and all. First of all, I thank all the members who work for the workshop. Me, I'm a beginner in the field of domination, but I get more and more knowledge or more ideas from this workshop. So I thank all persons, especially Manju ma'am and all others for giving such a wonderful workshop for all of us. Thank you.
Thank you, Vinci. Vijuma sir has joined, sir. Vijayuma sir, can you hear me?
Yes. I thought of telling towards the last because let others say.
Okay, sir.
I just saw but was muted, so I was wondering whether he is available. He has to give some concluding or presidential remarks.
If there are no other feedbacks, I think Vijayuma sir, you can have your comments, please. Deepalakshmi, do you want to say anything?
Yeah, ma'am.
Yeah, please tell.
Good evening, everyone. Really, we have gained a lot. Here, all the lectures, it's well ordered. Again, with great persons. You have, designed the program. So it's highly informative. Really, I'm having a page of to-do list. Really, you ladies rocking actually. I don't know how you are getting fund for conducting these kind of events, but it's very complete. I'm having so many things to do further. Once again, I'm actually silent watcher of you people. I know few of you from 2018 itself. Really, Vijay Kumar sir's research family, it's shining actually. Still here, 12th student participating the event. So on seeing this, it's really due to Vijay Kumar sir. I know about him. In many workshops, we used to get one booklet from Vijay Kumar sir. It's about for 11th, 12th grade students. So what are all exams they can appear for their future studies. So for like that, I used to get some booklet from him. If possible, please share that updated version. It's my request to Vijay Kumar sir. So, again, everything is so nice. Okay, ma'am. Thank you. Thank you for your. Yeah, thank you, ma'am.
Some message was there at the chat box, but now I can't see that message. On the second day, second session was Armugam sir's session. No, I am not seeing that message. That's why I replied. Oh, you are asking about the 22nd session. Yeah, that was Tijo sir's. If there are no other feedbacks, let me invite our teacher, our dear teacher, Professor A. Vijayakumar sir, for having his valuable comments or remarks.
I think Manjunath has something to say.
Yeah, exactly.
I think so.
Manjunath sir, please. No, sir.
Okay, so well done. It's the one word which I can use at this point. No event is perfect, but this is very near to perfection. As Manju Menon rightly pointed out, organizing a webinar is more difficult than organizing a physical event. We may be comfortable, our system may be, and our line connections may be okay, but that doesn't mean that all the 80 people had got it actually. So that's a major problem. And those who came from abroad to speak in this forum, they have been our friends since many years. For example, Sandy is known to our Cochin University group for last 15 years. So most probably they will accept unless they are very busy. So the coordination and the unified theme in which this discussion was focusing is a good sign that those who want to really get some problems and try to solve. We don't claim that all the open problems are easily solvable, but you found the common type of problem both in power domination and Raman domination. Just now, Dr. Anu presented, looking at the subgraphs, induced subgraphs, and getting a comparison between the parameters of induced subgraph and the full graph. So such related themes are there. And as a whole, I will rate the event as I'll give 9 out of 10. So that is the thing regarding the organization. Now, what Dr. Deepa Lakshmi mentioned is not in my hand. I am no longer the regional coordinator for the Math Olympiad because I was using the fund of Math Olympiad to produce that document. But the most recent is 2018. I don't know, Dr. Deepa has this version. If she doesn't have, she can write to me, email me, and then I can send you the brochure of 2017-18.
Okay, sir. Okay, sir. Thank you, sir.
I think now Pannuswamy is taking care of that.
No. Now the coordinator for Kerala is my colleagues in Maths Department, Dr. Naufal and Dr. Ambali.
Okay.
And the entire system has changed. We have PRMO, pre-RMO, RMO, INMO, and IMO. In fact, IMO result was declared yesterday with China getting maximum points and followed by Russia. So Chinese are always number one wherever they are. Okay, not only in COVID, but also in Olympiad since many, many years. So, and coming to the choice of Niranjan as a participant, it's a very good sign that you are admitting +2 students. What is the course they are now undergoing is immaterial. Okay, I have one case of organizing a quiz competition in Cochin University long ago, when there was one boy, I'm very proud to name his, tell his name, Raziman from Calicut, who attended single-handedly the quiz program of Mathematics Department, while others were having 2-3 members. And obviously, Raziman got the first prize, and he took away the shield and cash prize. So he was a +2 student then, and first rank holder, topper in the Olympiad. You know where is he now? He is in Switzerland doing his postdoc. So that is his position. So from Calicut to Switzerland, the journey was not easy, but they have reached the point. So it would be good if Niranjan, see, when you asked him what is your future plan, the answer was very clear. That is Oxford, Cambridge, such universities, or CMI, the best in India, or ISI. So I like such answers because the vision is very clear, no clouds in between. So the answer was very clear that I want to become. So there is a saying, birds fly because they think they can. Okay, so that is the confidence that you should have while answering, especially the younger you are, the more confident you will be, and later on you will realize that the confidence level is coming down because you know that there are more things to be explored than what is known. Okay, so it's an open call to all the participants. You are free to contact us for any research problem that you may come across. And if you want to connect with people also, thanks God, Cochin University has a very good connection with all the people all over the world. So if you want to connect with people or to your own research, you are free to collaborate with any of the speakers or other members of this group. And I wish you all the very best. You can expect another better activity from St. Paul's College within another 2-3 months. So they are very vibrant. The principal, Dr. Savida, Dr. Pramada, Nisha, they are all trained from Cochin University. So they will do it, I am sure, and they will do it better each time. And wish you all the very best. Thank you.
Thank you, sir. So the last one is definitely a word of thanks. The list is definitely, a long list, but I'm making it a brief one. Sincere thanks to all the speakers and definitely to all the participants who have joined for all the sessions on time and asked very nice questions. You were active throughout the sessions, most of you. I could see most of you because as we said earlier, you are at the comfort of your home, and many things are going on through your head that we know very well. So first of all, on behalf of the organizing committee, let me thank all the organizers, especially Vijayakumar sir, for all the helps from his side, and dear participants. Then definitely the Ramanujan Mathematical Society, who have supported us academically. I mean, this is a third event in collaboration with Ramanujan Mathematical Society, and thank you, Ramanujan Mathematical Society, for the support you have extended to us. Then for all the sessions, you were hearing a beautiful voice. That is our Bernice. She's our MSc student. Thank you, Bernie, for all your helps throughout the conduct of this workshop. And the department, all my colleagues from my mathematics department are here, including our principal, Dr. Savita KS. So I thank each one of you, from the principal and to each one of you, a word of thanks for all the helps, for everything. Thank you so much. So I think we can wind up the session. We will take all your suggestions that you have given in the feedback link in our future endeavors. Thank you all. Thank you very much. I think you can leave the session now.